Okay, hey everybody. So as I was just saying, today we're doing deeper NLP, which is an appendix topic, but I do think it is very worthwhile to talk about. Also, if you are thinking of doing the NLP project for phase 4, you don't have to incorporate this into your projects at all. I just think it is good to know if you're doing a capstone that includes NLP, then I might ask you to incorporate this into your projects as well, but no need to do this for phase 4, but if you're doing NLP for your capstone, I do highly recommend trying to incorporate some of this stuff into your project. So, okay. Oh, and also, just so it's in the recording, I'm going to put a poll in a couple hours on to Slack, and if you could just indicate what project you would like to work on for phase 4, just so I can start pairing you all up. Okay, so to get started, I actually want to start with a slideshow, and I've linked the slideshow over here. This is actually from another instructor, and I think they just put it together really nicely, so I'm going to use their slideshow. And then I'm going to walk through two main things, word vectors or word embeddings using two different libraries. So I'm going to show you all what word vectors are and how they work and how you can use them. And then I'll also go through like a quick classification process using word vectors. Then I'm going to talk about topic modeling, which is basically the thing I was talking about yesterday, where you can kind of soft cluster your text data points. Cool. So to start, let's start with word vectors or word embeddings. So word embeddings is a subset of word vectors. Technically, what we did yesterday with our bag of words methods of like TF-IDF and count vectorizer, those are also word vectors. As anything that is a numerical representation of anything else is a vector. So those are technically word vectors, but you'll see that when people talk about word vectors, they typically mean word embeddings. And word embeddings are basically another way that you can kind of teach machines to understand things like context, nuances such as like sarcasm, tone of voice, things that can't really be picked up just from the vocabulary itself. So it's actually really interesting. This will touch on a little bit of neural network stuff, which we haven't really gotten to yet. So I think as we talk about neural networks next week, it'll make a little bit more sense. All right, so word embeddings, what is meaning? Very, very deep question. So few definitions of what is meaning. It is the idea represented by text, idea that a person wants to convey by using words, or even more abstract, it can be an idea that's expressed in a work of writing or any form of art. So how can a computer interpret language? So we talked about this yesterday, bag of words methods, count, vectorize, or TF-IDF, where again, there's no notion of similarity or meaning of individual words. Also remember what we talked about with bag of words, the order of the words in your text are not taken into context. I mean, as you saw with the data frame that we had at the end of yesterday, everything was just organized in alphabetical order anyway. So the order of your words is not taken into context. It really only does give context of an importance in a corpus. So for example, the words Plaza Hotel and Waldorf Astoria should have high similarity, but something like count vectorizer or TF-IDF might not be able to know that unless you are maybe classifying like hotels, things about hotels and things about something else, and then you just have a lot of words that are associated with hotels. Another way for computers to interpret language is the most inefficient way of pretty much keeping a log of the meaning of words. So synonyms is one way to do that. So synonyms, again, it's only true in certain sentence contexts. Like I think if you look up any synonym for any word, you'll see a lot of the words can be used in very different contexts. So synonyms is not a straight, like, same meaning can be used in all the same ways. Synonyms are also very subjective, and it's also very hard to update with new words and slang, as well as manually upkeeping a thesaurus. So if you imagine, I think one of the older ways to do language processing is you literally have like a dictionary where you map similarities of words with some sort of measure. And this was all done manually. And every time there are new vocabulary words, this had to be manually updated. Cool. So we level up to word embeddings. And word embeddings, actually, if you were to look at word embeddings, is just a vector of numbers. And word embeddings don't really mean anything if we were to read those numbers out, but you can rest assured that they do represent your text. So word embedding started as with this idea of distributional semantics, whereby a word's meaning is given by the words that frequently appear around it. So when a word appears in a document, its context is the set of words that appear nearby within a fixed size window for you to decide. So in this example, let's say we want to have the computer learn the meaning of the word banking. Every time the word banking shows up, and in this case, we're going to set a window of ±5 words. So we're going to look at the 5 words before it and the 5 words after it. And basically, these become the context words. So the computer is going to kind of indirectly learn the meaning of the word banking and how the word banking is used, and also what banking could be referring to by looking at, these windows. And so these context words, words like government debt problems or crises or Europe, regulation, India, system, things like that, all of these context words will basically represent banking. And how a computer gets to learn, nuances and little ways that a word can be used is by training things like this over very, very large corpuses. So we're actually going to take a look at an example later that was trained on the entirety of, I don't know if it's the entirety, but it was trained over millions of Wikipedia articles. And you'll see a lot of these like word vectors have been created by that. So after the machine looks at a lot of occurrences of the word banking, it forms a set of numbers, a set of vectors, and these vectors are all going to be relative to each other. We'll see some more examples, so this will start to make sense later. Once a computer has done that, it will basically be a vector of numbers that will eventually represent the word banking, and we'll actually see some examples of that too. So what is exactly happening here? Neural network. So the way that this vector is created is through a neural network. It's a shallow one-hidden layer neural net to compute a dense vector representation for each word. That sentence will make a lot more sense next week. Basically, it captures the meaning of a word in a corpus using predefined windows of words. And there's 2 different ways to go about it. I'm going to briefly talk about this. And again, as I mentioned before, there are readily available pre-trained embeddings on different corpora such as Wikipedia and Google News. So as you can imagine, let's just say that I train some word embeddings to learn things from a set of like academic books. These word embeddings can look very, very different if I were to train a bunch of word embeddings on someone's like Twitter feed, for example. And there are actually word embeddings trained on Twitter as well. So typically, because word embeddings are all relative to each other based on what they are trained on, results don't differ by very much. But if you want to get very into the nitty gritty and do something very, very specific, then you might want to train your own word embeddings as well. The lab that is on word embeddings in our curriculum actually has you training your own word embeddings, which is really cool. But today I'm just going to talk about using these pre-trained word embeddings. So these word embeddings already exist. You just have to load them, download them, and you'll see how it works in a little bit. Cool. So these are just 2 ways that a neural network slowly learns the meaning of words. So the 2 ways are pretty much the opposite. This one is called continuous bag of words, where you input the series of words that come before and after the target word. So for example, the input being pineapples are and yellow. Go into our neural network and we'll output the word spiky if we want to learn the word spiky. And then skipgram is pretty much the opposite. This right now doesn't really make sense for us, but just good to know. Cool. So as a result, we have these word embeddings. They're really, really interesting. I think I talked about this very briefly when when we talked about linear algebra at the start. But word embeddings, if you were to take a word embedding, and typically they are of the length 50 to anywhere from 50 to like 3 to 500, basically numerical representation of a single word or phrase or sentence or chunk of text. If you do something like PCA and lower them down to a lower dimension, you can actually visualize them. And we're actually going to do an example of that in the notebook later on. But you start to see patterns arise, which are super interesting. So superlatives, for example, if you were to plot the word embeddings of the word slow, slower, slowest, short, shorter, shortest, you see that the direction when you go from like, the root word to, I forget what these are called, like the ER word and then the EST word, they all kind of follow a very similar pattern. And this is learned through the word embeddings as well. So they know that the relationship from slow to slower is similar to the relationship between strong and stronger. With word embeddings, you are also not restricted by vocabulary anymore. So for example, because of the way that word embeddings are trained, it can be on it can be on proper nouns as well. So a lot of word embedding libraries have proper nouns as part of their corpus that you can use. So for example, this is company to CEO, and you can see that they're all kind of that flat across line relationship. And yeah, so this is just like a very brief overview of word embeddings. Any questions at this point? And I'm going to walk through the implementation of it right now. Okay. So this notebook, I actually just pushed this notebook up about 20 minutes ago. So sorry for that. I'm also not going to be running this notebook because some processes take a very, very long time. I think I pre-ran this, so hopefully when I try and run things later, it won't break. But we're going to be using two main libraries to take a look at word vectors or word embeddings. So the first one is GenSim. And GenSim has an API within its library that you can load word vectors, and we'll see some of the cool things you can do with word vectors. So I've linked the documentation over here. This took my computer about, I think about 5 minutes to load. So if you're doing this, don't be surprised if it takes a little while. So here what I'm doing is I'm basically loading in all of the word vectors. And what ends up getting saved here is a giant dictionary of word vectors. So we've loaded these word vectors, and you can sort of look up words just like a dictionary, because word vectors is a giant dictionary. You can just look up words. So for example, if I'm looking at the word caffeine, this is the vector that represents the word caffeine, which is kind of interesting. So this is caffeine. If we want to look at another word like coffee, coffee also has a word vector. So it's pretty much loaded an entire dictionary into your Jupyter notebook. So all of these vectors have been pre-trained. I forget what this one was on. Let me take a quick look. Glove Wiki. Oh, if it's Wiki, I'm pretty sure it is trained on. Let's see. I think it should be trained on Wikipedia. So Glove Wiki GigaWord, I'm using this one over here. It's basically trained in 2014. So articles on Wikipedia in 2014. Here, I think it's 6 billion tokens. 6 billion tokens, let me just double check real quick. Yeah, 6 billion tokens means that there are 6 billion unique words in this library. And over here, oh, just kidding. It was trained on 6 billion tokens, and you have 400,000 unique words. This 100 that ends over here, it basically means that each vector is of length 100. So every word will be represented by 100 numbers. If you were to look at some of these other ones, if you were to look at the 200, it means that each word will be represented by 200 numbers. The pros and cons of using either of these, the more, the longer your vector is, the longer your models will take to run. It's just more columns, more features. That's one con, but the pro is you have a little bit more granularity. Because with 100 numbers, you can represent something one way, but with 200 numbers, you can represent that a little more, I guess, specifically. So these are all the different word vectors that you can actually load through GenSim, and they are trained on different things. So for example, this was Wikipedia 2017. You can see here there's a bunch that were trained on tweets. What else? I think Google News is another one. This one is just a Russian one too, so that's kind of cool. So yeah, these are all pre-trained word vectors. Cool. So what can you do with word vectors through GenSim? GenSim's word vectors, they have a lot of built-in methods that are pretty neat. So for example, you can actually look up most similar. So I think this should be able to run. Cool. So words that are most similar to coffee, they'll actually give you the 10 most similar words. I think you can also ask for more, but I don't want to look up the hyperparameters right now. But they'll show you some similarity metric, and then what are the words that are most similar to coffee. So tea, drinks, beer, not surprising at all. There are also proper nouns, as I mentioned. So Hilton, which is the hotel chain, you can see most similar. There's hotel, Vegas, Marriott, Sheraton, Hyatt, so on and so forth. So that's something that's pretty cool. Most similar can also get a little bit more, you can get more granular with that. You can also kind of do like, not really analogies, but you'll see what I mean. So let's just say we want to look for words that are most similar to woman and king, but not a man. So this is really interesting. It'll give you the result queen. And I thought that was kind of cool. Sweet. From Jensen word vectors, you can also do analogies. So I guess this was analogies. So we had, what is analogous? Japan to Japanese, Australia to Australian. You can see here there's Zealand for New Zealand, British, Australians, so on and so forth. And there's a couple other examples over here. So Australia, beer. France, you have champagne, wine, cognac. That's pretty cool. And then, yeah, just a bunch of other analogies here that you can play around with on your own if you'd like. You can also do odd one out, which is pretty cool. So England, France, Germany, Russia. If you do a dot split, it actually says the odd one out is England, which is kind of funny in the context of Brexit. But cool. Any questions at this point and like understanding word vectors? I kind of liken word vectors to like, you know how in PCA, after you do PCA, like the numbers don't really mean anything on their own, but it's the relationship between the vectors that become more meaningful. Cool. All right. So far we've only been dealing with singular words. With GenSim specifically, the way that you can use word vectors in a bigger, for larger pieces of text, like for example, the text classification examples that we've been doing, is you can turn it into sentence or document vectors. Through GenSim, this is the way to do it. And I'll actually show you this other library. I will say now that the other library that I'm going to show you all after this, that's the method that most people end up using. But to go with this, let's just say we have this sentence over here. I like my coffee hot. So here what I'm doing, I'm just doing a for loop over here for word in sentence.split. And I'm just going to append the word vector over here if the word vector exists. So not every word has a word vector. I think literally the word I doesn't have a word vector. Let's check. Word vectors. I. Oh, okay. I guess it does. Cool. Yeah, I guess it doesn't have it in uppercase, but doesn't matter. So just in case there's a word that doesn't exist in this 400,000 word dictionary, I have this try and accept. So what I'm doing here, and this is one way to represent an entire document as a vector, is I am just appending each vector to a list, and then I'm summing the list together. And when I sum the list together, it'll basically element-wise sum everything together. So if you have 5 words and each of them is represented by 100 numbers, I'll just sum all of those together. Now, pros and cons of that. Pros, very, very easy to do. You're just summing your vectors together. However, cons, if you think about this method of doing things, it is still very similar to a bag of words method, because in this method, we're still not taking into context the order of the words, right? Since we're just summing them together, context of like the order of words, not taken into account. However, now we have embedded meaning in this vector versus something like TF-IDF or count vectorizer. Also, when you have word embeddings, you have no sparsity because every value is a value that isn't 0. Cool. So this is one way to do it. Most people do not do this, but feel free to try it out. If you want to just test this method, you can as well. Cool. Now to look at a graphical representation of a bunch of words, and this is kind of similar to what I was showing you all over here. This is a function to plot out PCA word vectors. So again, these word vectors are all of length 100. That means 100 dimensions, so you can't really see them. But what I'm doing within this function is I'm getting the word vector, and then I'm also then fit transforming them into 2 dimensions using PCA. So this function, not super important, but you can see that I'm giving it a list of words. And this list of words are just random list of words. And after doing PCA on these word vectors or word embeddings, this is how they're plotted out, which is super interesting because if you take a look and see the distribution of these, they kind of group together as you expect. So like over here on the top left, you have more of like the food and drinks, right? You have like spaghetti and meatballs are also closer to each other versus like pizza, which is interesting. I think borscht is a soup. You have drinks over here. Over here, you have like places like France, Germany. I think like Europe happens to be over here, China here, Australia here. Here you have like institutions, and all of these are kind of like places, which is cool. And then down here you have all your animals as well. So I thought that this was really neat. The fact that you can start to see based on the word vectors, yes, those word vectors, these numbers mean nothing, but it's about the relationship between your word vectors that become very much more meaningful.
So does that mean that a lot of people eating pizza also drink brandy? Can you assume that from this?
I guess so. I guess so. So based on this, yeah, I guess the words that appear around the word pizza are quite similar to the words that appear around brandy. So yeah. All right, any other questions about this library before we move on to the next one? Cool. All right, so the next library is Spacey. And I'll admit Spacey actually last year went through a major upgrade and I haven't had the time to look into the upgrades myself. So this is an older version of Spacey that I'm using. The newer version is actually even more streamlined. I've had a couple students earlier this year work through the new version's documentation, which is apparently easy to read. If students can do it for their capstone, then it shouldn't be too hard. But I've had a couple students work through that. The newer version of Spacey is way more streamlined than what I'm about to show you all. But this version still does work. Okay, so what I'm using here is Spacey also has their own pre-trained word embeddings. If you uncomment this line, this will help you download those word embeddings. And we're actually going to apply Spacey to a text classification problem, the same problem that we had yesterday, actually. I don't think I have classification in this notebook, though, but it's just the pre-processing steps. So what we're going to use is Spacey. TQDM is something that is actually not specific to NLP, but it's kind of like a progress bar for loops. And you can actually use this for any sort of Python function that is looping anything. So TQDM, if you ever need to run like a super long for loop and you need to know how long that's going to take, TQDM will show you. And I'll show you what TQDM kind of looks like. So first we have our data set, same data set from yesterday. And we take a look at the shape, and this is where we do the word embeddings. So first I'm loading in the word embeddings, and I'm actually calling it NLP. Spacey's documentation actually calls their word embeddings NLP as well. And this is super cool. What I'm doing is I'm applying, progress apply basically is the TQDM, but I am applying NLP onto my body of text. So in just this one line, it creates document embeddings, which is super cool. So from that, you'll see that this is the original text, and this is the Spacey version of text, which right now doesn't look like word embeddings, but we'll see. It's actually very, very cool. So difference between Spacey and Gensim is this way of doing Spacey actually does take into account a lot of things. It takes into account the order of your words. We'll actually see that you can get a document vector and you can get individual word vectors as well. Also with Spacey, they actually prefer that you don't do any text cleaning unless there's something that you don't want it to see. But things like lowercase, you actually shouldn't do that with Spacey because it wants to recognize uppercase, lowercase. Spacey also takes all caps into account. So like if you're like angrily or excitedly saying something in all caps, Spacey will take that into account as it's doing its vectors too. Spacey also recognizes emojis and symbols as well. So you actually don't have to clean that data out if you want to use Spacey too. So it's trying to infer meaning from the way that you're typing out your words too, which is super cool. So literally through this line, we end up with this. So let me just run this real quick to hope. Okay, good. So let's take a look at the first element of Spacey to just see what is being stored there. So what I'm doing is I'm grabbing the first element over here, and you'll see first Spacey, which is what I called it. First Spacey is if I were to just output it, it's just the text itself. However, if you take a look at the type of it, and the type of first spacey is a spacey document. And then if I were to look at the specific word, so if I were to look at the first word, it actually does it as, it actually breaks it up into words that you can actually index. So if I take a look at the type of the first word, it is a spacey token. And each of these data types actually has a lot of functionality. It can do all of the functionality that GenSim did actually as well. Like you can do like most similar, things like that. So if I actually quickly look into token over here, you can see that this is the new spacey documentation. But here you can see attributes. You can get like, I guess the text itself, a tensor, that's cool. The vocab object, the token's norm, lowercase, shape, is alphabetic, things like that. So you can actually do you can actually use a lot of these out of Spacey. I want to look for the methods. Spacey methods, I hope they have it here. All right, if it's not over here, somewhere in the documentation, because they've since changed it. Somewhere in the documentation, you can basically do like get most similar or most different, things like that. Okay, so let's take a look at the vector. So this specific one that I downloaded is the medium size one, and this medium size one, each vector's length is 96. Why it's 96, I don't know. But you can see that from here, if I take a look at the vector for the document, so this is first Spacey's vector, we get this vector of 96. And this represents the entire document, taking into context things like uppercase, punctuation, the order of your words, if there is any use of like emojis, all of that is taken into account in this vector, which is so cool. Through that, if you ever wanted to just get the specific word vectors, you can do that as well. So over here, you see I'm doing first Spacey.vector. I'm getting this vector that represents the entire first document. You can also get the word vector. So first Spacey index 0.vector gets me the word vector for that first word noting, I think. You can get part of speech tags, which is pretty neat. So if you take a look at first Spacey again, first Spacey is like this, and you can get the part of speech. So if you ever wanted to filter by part of speech, you can use it through Spacey as well. Let's say you only want to keep like adjectives and adverbs. If you were looking for like descriptive words, you can actually filter it this way, which is really neat. So you can get the part of speech. So it'll be what verb, I actually don't know, conjunction, I have no idea. Determinate, is that what that's called? Noun, proper noun, proper noun. So Spacey knows all of that as well. Cool. So how do we put this into our modeling? All we have to do is just take all those vectors and put them into a data frame. So just like this, I'm using NumPy VStack, but you can pretty much use any method of concatenating your arrays into a data frame. But yeah, just like this, I have 1,000 rows and 96 columns of my word vectors, and this will be the data that goes into your modeling. Now, huge pros and cons, right? One pro is that you're taking into context meaning now, where yesterday's methods we could not. But one huge con is like, this is not interpretable at all, right? Like from this, if I print out my most important features, it's just gonna give me like a bunch of, all right, vector position number 5 is most important, you know? So because of that, word embeddings, a lot of pros and cons. You're taking into account a lot of things, but you lose that interpretability. So keep that in mind. If it's important to you to know what words lead to what kind of classification, then you probably don't want to use word embeddings. Or if you think that the problem that you're trying to solve doesn't really have to do as much with context, rather more of the content of the text, then maybe you don't want to use word embeddings either. But word embeddings are getting much more advanced now. So that's cool. All right, any questions on word embeddings before I talk about topic modeling, which is that clustering thing I talked about briefly? Okay, so topic modeling. Topic modeling also comes out of GenSim, so that's nice. And what topic modeling does is it actually makes use of word vectors to kind of extract main ideas of text that is being represented in your entire data set. So here I have 1,000 data points or 1,000 pieces of text. Of course, some of them is satire, some isn't, but doesn't matter here. You can actually do topic modeling for each class separately as well if you want to gain that kind of information. I'll show you what the output looks like. First, I'm processing the words. This process, not so important. I think somewhere I have linked, okay, I don't have it linked, but I'm gonna send out a walkthrough for creating the topic modeling if you would like to see that. So for topic modeling, annoyingly, the way that your data has to be is like in a list of tokens, like that, basically. And you have to do a bunch of other pre-processing steps. But when you train your model, so what we're doing over here is we're building an LDA model. So the model that does topic modeling is known as LDA, which stands for Latent Dirichlet Allocation. And what it's doing is it's just trying to figure out what the main ideas of your text is, or text are, I don't know. The main thing that you have to care about is how many topics you want to extract. So similar to all the clustering methods that we talked about before, you have to tell the model how many topics you want to see. So in this case, we're just going to start with 4. So this takes a very, very long time to run. I've run topic modeling models that take over 7-8 hours to run. So this is a long process, so be prepared for that if you want to do topic modeling. But from that, you can see that I have my topics. Very similar to clustering as well, and this kind of goes off the page, so I won't go into each one specifically, but similar to clustering, you kind of have to name the topics yourself, but not similar to clustering. They actually show you the makeup of each cluster or each topic. So this is one way that you can output it, which is just like this. And basically this is saying for topic 0 is made out of these words like year, country, also percent, blah, blah, blah. Second topic is more these words like government, would, official, election. This next topic, it's like people, police, kill, migrant, protest. Third one is communication experience. So you can sort of see that they're trying to separate these main ideas. So this is a little hard to read. So pretty much everyone that does topic modeling uses this thing called PyLDA-Viz, which is really, really neat. So again, LDA is the model that's doing this separation of topics. But we have this really nice interactive output that you can get just by plugging in your information into PyLDA-Viz. So this is what our output shows. I don't want to like mess around with too many of these just in case it's not run. This isn't run. So this is from the last time I ran it. But basically our 4 topics are distributed like this in our interdimension into our PCA space. So you can see here, this is PC1 and PC2. And you can already see that we have 4 topics, but 3 and 4 are right next to each other. And you can literally use this distribution to talk about the similarity or disparity between topics. So maybe based on this, I should lower it to 3 topics. I don't know, we'll see. But this is really neat because as you hover over each one, you can sort of get an idea of what the topic is made out of. So you can see here, it's like say government, would, official, basically the same thing as last time. And if you go into a specific word, you can see like how important is each word to other topics. So for example, if you look at this word could over here, it's in it's in topic 1, but also a little bit topic 2. The word political is very much in topic 1. Things like election, topic 1. Let's see if there's another one that is, yeah, the word force is a little bit in 2 and 3 as well. And you can sort of see this based on these like bar ratios. But yeah, this is a super great EDA tool for your text data, in my opinion. But yeah, I'll link that walkthrough in our Slack channel later today as well. But yeah. The math behind LDA is very, very complicated. To be honest, I like started to look into it and then I gave up. So I actually don't know exactly how LDA works, but it's quite similar to, it's like a combination of it's kind of like PCA, but it's like PSNE, which is the other one I was talking about that looks to separate as much as possible. So it's very similar to that. Cool. All right. Any questions about this stuff? Awesome. Again, I want to preface by, not preface, but I do want to say that in your phase 4 projects, I don't need to see any of the stuff that I talked about today, because I think just doing the first part of NLP is kind of a lot of work for a 1 week project as well. So just so you all know. All right, if there are no further questions, let me stop this recording over here